This presentation is called Design and Seismic Analysis of Mechanically Stabilized Earth Walls. This is to complete coursework at the University of Idaho for CE 566 Earthquake Engineering. Mechanically stabilized earth walls are seen on many highway embankments across Idaho. They often appear as large interlocking block patterns. As you go down the freeway, you'll see them oftentimes in cuts. They hold back huge quantities of earth, and they're built because they're economical, they're flexible, and they're durable. In this paper, we will introduce some MSE wall designs, look at the Federal Highway Administration design and seismic analysis methods, discuss internal and external stability, and discuss recent developments from two recent research papers. Common to most MSE walls, they have compacted granular backfill, they have some kind of a face wall, they have reinforcement extending into the soil mass, and that reinforcement is called a soil inclusion. An extensible reinforcement is a definition that's used. It refers to deformation of failure of the reinforcement is much less than the deformation of the soil, and extensible reinforcement is reinforcement where the deformation of failure is comparable to or greater than the deformity of the soil. Typical MSE wall has interlocking cast blocks. There's a face wall connected to mechanical reinforcement, which can be metal, geosynthetic fabric. Typically, a reinforcement is extended 60 to 70% of the wall height into the compacted soil layer. There's also some other types of MSE walls which we'll discuss. Here's a section through a typical MSE wall consisting of face wall, reinforcement, granular backfill, and the random backfill that you're holding back. I'll briefly discuss a few other types of mechanically stabilized earth walls. I'll show you those on the next clip. Here's a sketch of a few of the types of MSE walls that I've just talked about. Now that we know the different types of MSE walls, I'd like to briefly discuss the FHWA design guidelines. They want us to analyze the working stresses and check the stability of overall structure and to perform deformation evaluations. Included in that is checking reinforcement location and stresses in the soil and the reinforcement, and overall stability of the structure, external stability, internal stability, and combined stability. Note that there are specific guidelines for reinforcement using inextensible reinforcement or extensible reinforcement. Also, need to consider if earthquake should be considered, and to determine that, you look at the acceleration coefficient, and FHWA recommends that the acceleration coefficient is less than 0.05, then the seismic analysis is not required. Now we'll focus on external stability analysis, and it refers to checking the wall for sliding, overturning, bearing capacity, and deep stability. And is to include the soil seismic forces P sub AE and P sub IR. P sub AE is the soil mass retained behind the reinforced soil mass, and the P sub IR is the inertial force of the reinforced soil mass itself. You can see on this slide the graphic representation of the forces I talked about. The P sub AE force, the P sub IR, the inertial force. Also, it shows up in this slide the static force F sub T, and I'll talk about that next because it's combined with these other forces. So the earthquake force from the soil mass behind the reinforced earth is calculated as shown. It's called P sub AE, and the inertial force P sub IR is calculated as shown, and that's the inertial force of the reinforced earth mass. The F sub T force from the retained soil mass also has to be added in. The combined forces are shown in the previous figure, and only half of P sub AE is used to account for the maximum forces not occurring simultaneously during an earthquake. For internal wall stability, two scenarios must be checked: failure or elongation or breakage of the reinforcements, and failure by pullout of the reinforcements. The internal stability of the MSE wall depends upon seismic forces and static forces in the reinforcement zones. Seismic load is just basically the inertial force from the active zone pushing on the wall. The active zones for extensible and inextensible reinforcement are a little bit different, as seen in the following figures. The maximum static tensile load per unit width is figured out using equations from FHWA. It's called T sub max, and T sub MD are the inertial forces distributed throughout the reinforcing, proportional to the length of the reinforcement. So the maximum tensile force in the reinforcement is T max plus TMD. Then the stability of the wall with respect to breakout and pull out is calculated using the Federal Highway Administration guidelines. And you'll note in the equations that a seismic safety factor is 75% of the minimum safety factor, static safety factor, is used. Here is a sketch of the internal stability forces that we talked about. You can see the active zones for reinforced extensible reinforcements and inextensible reinforcements are slightly different, and the other forces we talked about are shown on the figure. We looked at two research papers. One had to do with facing contribution to seismic response of reduced scale reinforced earth walls, and the other one was external stability of reinforced soil walls under seismic conditions. The first paper came to some conclusions that the FHWA designs do not consider face wall vertical loads, and additional loads could lead to unsafe wall performance, and that stiff wall faces resist dynamic loads. Current practice leads to underestimated wall load capacity. They also found that current FHWA methods poorly predict size and distribution of the connection loads. Design methods significantly underestimate total earth forces. They also found that falls excited closer to fundamental frequency, the displacements and reinforcements are much greater than when excited about a distant predominant frequency. And authors felt that the current methods do not give accurate predictions of reinforcement loads and distributions based on current testing. They felt that further work needed to be done before they could use these results. In the second paper, external stability was studied using geosynthetic material, using a pseudo-dynamic approach. They changed vertical and horizontal accelerations, and they changed the soil friction angle. One of the results was that they found that the material length for sliding stability reduced with increasing friction angle. Other results found from the second paper were that the required length of geosynthetic reinforcement significantly increases with increases in vertical and horizontal acceleration factors. They also found that as the period of shaking increases, the factor of safety against sliding decreases and longer reinforcement is needed. And they also found as the soil friction angle increases, the required reinforcement for overturning resistance decreases. We can also see that more reinforcement is needed when horizontal and vertical accelerations increase, as the period of shaking increases. And we've also noticed that just the overall, this analysis method requires more reinforcement compared to the pseudo-static results. In conclusion, I've found that the Federal Highway Administration has well-established methods for design and seismic analysis of these walls. Performance has been good. The wall performance has been good in earthquakes. The referenced research paper indicates that better analysis methods are needed to incorporate pseudodynamic and dynamic test results, and increased reinforcement lengths are needed for the dynamic effects of earthquakes.